Replication is the process of creating and maintaining multiple copies of the same data. It primarily helps with fault tolerance. If one server fails, replicas can still serve traffic, ensuring data availability. Replication also improves read scalability, as multiple replicas can handle read requests concurrently. In this video, we will cover why is replication so important in distributed systems, what consistency guarantees should we consider before designing replication, and how do we design replication effectively. And by the end of this video, it will be clear why replication is so hard. Hi everyone, I'm Ronak and welcome to Renaissance. We first want to discuss why replication is so important in distributed systems. One of the main motivations behind building a distributed system is to improve performance. For example, imagine multiple clients making requests to a single server. As the number of clients grows too large, the server can become overwhelmed, leading to slower response times or even denial of service. A common way to improve performance is sharding, where we divide data and distribute it across multiple servers. However, maintaining more servers also increases the likelihood of failures. In distributed systems, we must assume that servers will continue to fail at a steady rate. To handle failures, we introduce redundancy through replication. Additionally, failover to replicas must be automatic, as human intervention is not feasible at this scale. Replication introduces a new challenge: maintaining consistency between replicas. Synchronizing state, keeping an exact copy of data across multiple replicas might seem straightforward, but as we'll see in this video, it can negatively impact performance and even availability if not done correctly. Ultimately, in trying to solve the failure problem, we end up facing the same performance problem. This cycle keeps appearing in different distributed system designs. Before designing replication, we first need to understand what kind of consistency we want in the system. If strong consistency is not required, we can design the system in a way that takes advantage of this flexibility to achieve better performance. Generally, three types of consistency are observed in distributed systems: no consistency, strong consistency, and eventual consistency. In no consistency, different replicas may have different data for the same state. Let's look at an example to understand how this can happen. Suppose we set up replication so that a client is responsible for writing data to all replicas, and the last write wins. Imagine a setup with two replicas and two clients. Two concurrent writes can arrive in different orders on different servers, leading to inconsistencies. These inconsistencies will persist unless additional measures are taken. In strong consistency, all instances always have the same view of the data. A good way to understand strong consistency is to imagine a single server handling all updates. Any client can write to it, but at any moment there is only one true state of the data. To achieve strong consistency in a distributed system, we need to extend this single server behavior to multiple servers, ensuring they behave as one unified system. However, maintaining strong consistency is challenging and can significantly impact performance. One approach to implement strong consistency is synchronous replication. Let's explain synchronous replication with an example. In this replication, clients write only to a single leader, which then forwards the write request to all replicas. The leader waits until every replica commits the write before confirming success to the client. While this ensures consistency, it hurts performance because every write must wait for all replicas to respond, and any slow replica will make it even slower. It also reduces availability. If even one replica goes down, the system may halt updates until it recovers. Later, we will explore how to achieve strong consistency with better performance and availability. A widely used approach in industry is eventual consistency, where different instances may have different data temporarily, but they will eventually converge to the same state. Here is an example using asynchronous replication. Suppose clients only send updates to a leader and each follower subscribes to this leader to receive updates. When client sends write to leader, it only write to its log and immediately send back success response to client. Not all replicas process updates at the same speed. Some may process updates faster than others, leading to temporary inconsistencies. At any given moment, two clients might read different data from different replicas. However, if no new updates are published for a while, all replicas will catch up and eventually all instances will have the same data. But data can be easily lost in this pattern if the leader processes a write but crashes before any follower can replicate it, resulting in another follower being promoted to leader without the latest update. Later, we'll explore how to achieve eventual consistency with better durability. Now, let's talk about how to design replication. Replication is generally implemented in one of three ways: single leader replication, multi leader replication, and leaderless replication. In single leader replication, all writes go through the leader, which is responsible for forwarding those writes to its followers. We previously discussed synchronous and asynchronous replication, both of which have their own challenges. To address these issues, a widely adopted approach is semi-synchronous replication. In this method, only a few replicas are kept synchronous, while the rest remain asynchronous. The leader waits for synchronous replicas to commit before returning a success response to the client. Meanwhile, asynchronous updates don't block operations and are replicated in the background. If some synchronous follower go down, an asynchronous replica can be promoted provided it is able to catch up. If the leader fails, a synchronous follower is promoted to become the new leader. This replication pattern offers high availability while maintaining low response time. However, leader selection in distributed systems is a challenging problem. One key issue is detecting leader failure. If a client cannot reach the leader, it's difficult to determine whether the leader is down or if there is a network partition. If a new leader is incorrectly elected due to a network partition while the previous leader is still active, a split brain scenario can occur. In this case, both nodes would process conflicting writes without a way to resolve the conflicts. The leader election problem can be solved using consensus algorithms, which we will cover later. Multi-leader replication consists of multiple leaders, each with its own followers. In this setup, clients write to multiple leaders, and each leader forwards writes to its followers as well as other leaders. Multi-leader replication is commonly used in multi-data center setups because cross-data center writes are expensive in terms of response time. It also doesn't make sense to use it within a single data center, as synchronizing state between leaders is complex and can lead to frequent write conflicts, requiring conflict resolution. Let's consider an example of a conflict. Suppose two clients in different data centers write different values for the same state at the same time. The leaders asynchronously synchronize data through a queue, where each leader pushes its changes. When both leaders consume data from the queue, they each receive a different value for the same state. If they apply these changes without any conflict resolution, both data centers will end up with inconsistent data. Another approach is time-based resolution, where a timestamp is sent with every change. If a leader receives an update with an older timestamp, it simply discards it. This ensures that all data centers have a consistent view of the data. However, this approach has a major problem. Time synchronization across servers is unreliable. We will dive deeper into this issue in a later video. Detecting conflicts is also crucial, and a common method for doing this is versioning. Each leader starts with the same version number for a given state. If a client updates the state, the version increments. If a leader receives an update from another leader but the version doesn't match its current version, it means the data was updated from a stale value. Conflict detection is necessary if an application wants to implement custom conflict resolution logic. A great example of custom conflict resolution is Git. A user pulls the main branch into their local branch and makes changes independently. When they attempt to merge it back into the main branch, Git detects conflicts if other changes have been made. Instead of automatically resolving the conflict, Git allows users to manually choose the correct resolution. Sometimes it's better to avoid conflicts rather than resolve them. One approach is geo-based writes, where certain types of writes are restricted to a specific data center. For example, if a user lives in Singapore, their writes always go to the Singapore DC, even when they travel. However, if the Singapore DC goes down, some form of fallback resolution is still needed to handle the situation. Ultimately, there isn't a one-size-fits-all solution for conflict resolution, which makes multi-leader replication challenging. Now let's talk about leaderless replication. Leaderless replication means there are no leaders, which effectively means everyone is a leader. In a sense, it is similar to multi-leader replication, but without any followers. We have already seen how difficult multi-leader replication can be, so for leaderless replication to work, we need a new concept, and it's quorum. In a quorum-based system, we define R as the number of servers to read from, W as the number of servers to write to, and N as the total number of servers. To ensure consistency, we must write to at least W servers and read from at least R servers. Additionally, we must maintain the condition R plus W greater than N. This ensures that every read and write operation overlaps with at least one server that contains the latest data. We can also use versioning to determine the latest data when reading from servers that contains both old and new values. Leaderless replication suffers from the same conflict issues as multi-leader replication. We already covered this in the no consistency section, where two concurrent writes can arrive in different orders on different servers, leading to inconsistencies. To address these issues, we need conflict resolution just like in multi-leader replication. This replication might also have issues with read-write consistency. If reads and writes happen concurrently, writes might not be applied to all replicas immediately. For example, suppose a client updates a football match result, setting Argentina's score to 1 goal. However, during this time, another user may still read the old data because the write has not yet been applied to all W servers. Even worse, the first read might return the latest value of 1 goal, but a subsequent read could fetch data from replicas with older values of 0 goal, making it appear as if the score reversed, which is a major consistency issue. Another issue arises when a client initiates a write to W replicas, but only a few accept the update because some servers are down. If the write fails, it is cancelled, but the partially written data may remain in some replicas until it is rolled back. Any reads that happen before the rollback may fetch incomplete or inconsistent data. We have explored different replication patterns along with the challenges they bring, especially around consistency and conflict resolution. As we have seen, replication isn't just about making data available. It's a constant trade-off between performance, fault tolerance, and consistency. In the next video, we will dive deeper into how distributed systems achieve strong consistency using consensus algorithms like Raft. So if you are interested in that, make sure to subscribe and stay tuned. Thanks for watching.